Okay, hello everyone, and welcome to this presentation, which will be about learning and adapting security policies in dynamic IT environments. My name is Kim, and this is joint work together with Professor Stadler at KTH. A big challenge that we see currently is that cyber attacks are getting increasingly automated, and they are also evolving very quickly over time. It is almost every day now that we see new vulnerabilities and new attacks being disclosed. And this trend, in combination with the trend that our infrastructures are also getting larger and more complicated, means that it becomes very difficult to manage network security. So the goal of our research in response to these challenges is automation and learning. In response to more and more automated cyber attacks, we want to automate more functionality also on the security side. And in response to quickly evolving attack methods, we want to have security functions that are adaptive, and we want to have security systems that can co-evolve with changing environments. To achieve this goal, we investigate self-learning security systems. So these are systems that collect data from their computing environment in real time and uses that data to make predictions and forecasts about the future, and then takes actions based on those predictions to meet different security objectives. And to build such self-learning security systems, we have developed a general framework, and that is the topic of this paper. So the starting point of our framework is that we have a target system. This simply corresponds to the system where we want to automate the security functions. Now, typically, this is a safety critical system, so this is not an environment where we easily can run experiments and where we can collect data. What we do instead is that we take the configuration of that target system and we emulate this in our emulation environment. This then gives us a controlled and also a safe environment where we can run experiments, so we can run different types of attacks, different types of defenses, and we can measure and we can collect data. This data we then use to do system identification, to identify a model of the system. And that model allows us to perform theoretical analysis of the problem and also to apply numerical methods to compute optimal or near optimal defender strategies. We then take the computed strategies and we evaluate them in this emulation environment again. And then we have this conjecture that since this emulation is a very close replica of the target system, namely it has exactly the same configuration and exactly the same software as the target system, therefore, we conjecture that the performance of a security policy implemented in the emulation here will be very similar to the performance that we can expect when we implement the same policy in the target system. So it gives us a very good indication of the quality of the policy. So that's the high-level overview of our framework, and this is something we have been working on for the last couple of years, actually. So this paper I'm talking about today should really be seen as an extension or as another milestone in this research agenda. And the particular problem we tackled in this paper is to learn in a dynamic environment. In our previous work, we have assumed that while the target system may be very complicated and may be very stochastic, we have assumed that it remains stationary over time. It doesn't change that much. However, we know, of course, that this assumption doesn't really hold in practice, because in practice, changes happen. Components may fail, bandwidth may fluctuate, and load patterns can shift, for example. And when these changes occur, we don't want that our security policy start degrading in performance and, for example, start giving a lot of false positives. We want the security policy to be automatically adapted to the changes. And that's the problem that we tackle in this particular paper, where the main contribution is a generic algorithm for adapting security policies to these dynamic changes. And this algorithm includes 3 parallel components that run in a distributed system. So first we have the digital twin, and we already discussed this a little bit previously. The role of the digital twin here is to track the changes from the target system that we assume is constantly changing, and also to collect data. Then we have the system identification process, which receives streaming data from the digital twin and should and should then continuously update the model of the system. And finally, we have the learning process, which takes the latest system model and then should compute the optimal or near optimal defender strategy. And these three processes we then deploy in a distributed system where they are coordinated via a parameter server architecture. To create a digital twin of the target system, we take each physical component and we emulate that with a Docker container. And we emulate the vulnerabilities and services and programs offered by the various physical components using software running inside the containers. We achieve isolation in the network and resource constraints using standard modules in the kernel. And we emulate arrivals from the client population using a Poisson process, which may be non-stationary. And finally, we emulate the network conditions based on previous empirical studies of enterprise networks. So for example, we emulate the internal connections between the gateway and all the nodes inside the infrastructure using gigabit connections with no packet loss. And we emulate external connections between the gateway and the attacker and the clients using 100 megabit connections with some packet loss. And following this relatively simple recipe here, we can take almost any target system and we can create a very realistic emulation of that, which we then can use to run our experiments, to run attacks and run defenses and collect this very important data. This data is then fed into the system identification process to identify a model of the system. We model these kinds of systems as discrete time dynamical systems, which have Markovian dynamics and are partially observed. So we assume that the system here has some state. This state is, however, hidden from the controller. So the controller can only observe observations that may be correlated with the state. So this typically corresponds to log files, alerts from an intrusion detection system, or perhaps CPU metrics and so forth. These observations are then fed through a filter or a program that computes a belief about the current state. So formally, the belief is a sufficient statistic of the history of observations and gives a probability distribution over the state space. So it basically summarizes all of the previous history of observations to tell us, okay, based on this history, what is the most likely state? And that belief is then fed into the controller, which will automatically decide which action to take next. So it's a closed loop feedback system. Now, this is a very generic model that we can instantiate in many, many different ways. And of course, we want to instantiate the system model to best represent the target system. And we ensure this by doing system identification. We don't have to identify the configuration of the system. This is already given to us. We already know the configuration. But what we have to identify is the dynamics of the system. So how does the system perform under varying conditions, under varying load, and also under varying types of attacks? And we estimate this unknown information based on the data that we receive from the digital twin. In this particular case, I used Gaussian mixture distributions to estimate the unknown distributions, but in principle, you can use any estimator here. And that brings us to the final step. So now when we have estimated dynamics, we have instantiated our system model, we can now apply our favorite numerical method to compute the optimal or near optimal defender strategy. So this could be, for example, reinforcement learning or a game theoretic method, or maybe dynamic programming or control theoretic method. In our work, we've actually designed our own algorithm here that is based on optimal stopping theory. And we have shown that this is much more efficient than the previous work or previous algorithms, state-of-the-art algorithms. But the framework itself is much more general, and you don't have to use our stopping theory formulation if you don't want. You can use any algorithm here or any optimization here. So putting it all together then, we now have a general algorithm with the 4 different components for automatically adapting security policies in a dynamic environment. So we have the target system, which is, we assume is dynamic and constantly changing. Then we have the digital twin that is tracking the changes from the target system and is collecting data. And then we have the system identification process, which is continuously updating the system model. And finally, we have the policy learning process that uses the latest model to compute the optimal defender strategy. And we took this system here, this architecture, and we applied it to the following use case, so an intrusion prevention use case. Here we have a target system that you see here to the right that consists of 30 components-ish, and are connected in exactly this topology that you see here. And we assume that there's an attacker here that's constantly attacking the system and making intrusions. And this attacker is also changing over time, and also the system is changing over time. So we want to see now, okay, using our method, first of all, can we learn how to prevent this attack? We assume that initially the defender doesn't know anything. And secondly, we also want to know, okay, given that we have learned how to defend the attack, can we then update this policy dynamically when the attacker changes? And we ran this for 50 hours in our testbed. And we can focus here on the bottom plot, which shows the performance of our method and comparison with baselines. So the performance of our method is shown in pink, and the performance of the theoretically optimal, in this case, is shown in the dashed black line. And the performance of the baseline method, or the previous state of the art, is shown in the green line. So what we can note is that our framework is very nicely tracking the optimal performance over time, which indicates that it is constantly adapting the security policy, even though the attacker is changing and the system is changing. And you can compare this to the previous state-of-the-art method in green here, which has a much more spiky performance and doesn't really track the optimal performance as nicely. Of course, much more details about these results is available in the paper and also in the references. To conclude, we develop a framework for automating certain network security functions. This framework includes emulation, simulation, system identification, and reinforcement learning. We have applied this framework to an intrusion prevention use case, and the framework rests on a very solid foundation in terms of hard results obtained from practical systems, and it also led us to several interesting theoretical discoveries and results. In future work, we want to extend this by closing the gap to reality. Currently, we have a very simplified system model, and we want to make this more sophisticated to better capture complicated systems. Thank you very much for listening.